In this final part of LS10, we're going to talk a little bit more about technology mapping. In previous lectures, we have already discussed technology mapping being step 4 of the 5-step systematic designing procedures. Technology mapping involves technology, which are available physical components at your disposal for you to implement your circuit. What you can do with these technologies depends on what kind of technology there are. And one of the things that you'll likely encounter in real life is something called a programmable implementation technology, field programmable gating array. What you can do with these type of technology is that first of all, you can write up your circuit design in something called a hardware description language. It's kind of like a programming language, but it's not describing a program, what a program would do, but it's describing what a circuit would do. And then you can take this description written in hardware description language, upload it to the field programmable gating array, and the field programmable gating array will work as the circuit you intended to implement. Aside from all this, it is also important to know some of the common things that could happen inside technology mapping. The basic physical gates that we encounter a lot about now, for example, AND gates, OR gates, and NOT gates. It is of vital importance that you understand alternatives to implementing these gates when they're not physically available. In some of the previous examples, we've already taken a look at implementing a NOT gate without using an actual NOT gate, but by using a NAND gate, an AND gate with an inverter. So, let's take a look at some more examples of that. In this slide, you find some of the information that you can use in real life. For example, in certain cases where you don't have an AND gate, what you can do is to replace instances where you need AND gates with a NAND gate. Because the NAND gate is essentially an AND gate with an inverter, what you can do is you can add another NOT gate ahead of it, as you can see on the right hand side. You can use this combination to replace your pre-existing AND operators, and similarly you can also replace an OR gate with a combination of NOT gates and NAND gates. This is just by applying De Morgan's law. On the example at the bottom over here, we also have a replacement of the AND gate using a NOR gate, not NOR gate, as well as some NOT gates, also by applying De Morgan's laws. And finally, we have the OR gate being replaced by NOR gate and another NOT gate. All very standard procedures. The concept of technology mapping in practice, let's say in this particular case you want to implement the circuit diagram on the right hand side using NAND gates and inverters only, which is actually how FPGA boards are which is similar to how FPGA boards are designed in practice. What you would end up having is a series of NAND gates or NOR gates and a lot of conditional inverters which only invert values when receiving specific inputs. What you would do is first of all figure out an alternative to all of your components such as AND and OR gates. You can find information on how to replace AND gates and OR gates with the NAND gates on the previous slide. For the AND gates, we can simply use NAND gates with an additional NOT gate. The OR gate is a little bit more complex, but you can still accomplish that by using the combination of NAND gates as well as a series of NOT gates, such as over here. What you would do in this instance is that you would perform replacement and then perform further simplification, because as you can see, NOT gate number 5 is kind of inverted again by number 7 and number 6. NOT gate number 1 is inverted by NOT gate number 2. NOT gate number 3 is further inverted by NOT gate number 4. All of these duplicated operations can be simplified. You can simply eliminate NOT gate 1 and NOT gate 2, NOT gate 3, NOT gate 4, and 5, 6, 7 altogether to make the whole process a lot easier, because again, double negation is, well, basically just positive. You perform further simplification, and then you have the final simplified result. This step is quite important because in technology mapping, as you discover more available physical components, sometimes you're aware of the presence of these physical components when you're optimizing your circuit, sometimes you might be not. This is why, even though we call it a 5-step systematic designing procedure, sometimes you do need to go back and forth between technology mapping and optimization, even though there's no error or there's no bug being found. This is likely one of the questions that will, for example, happen inside an exam or one of your assignments. One of the two steps are likely to go back and forth with one another inside the 5-step systematic designing procedures. This is referring to technology mapping and optimization. Depending on the technology you have at your hand when you're trying to do technology mapping, the way you optimize your circuit could change a little bit. This also includes when you're trying to use hierarchical design. In hierarchical design, usually you would have a pretty good idea on what kind of subcomponents you would want when you're doing optimization. And then you would implement it and then apply them in technology mapping. And sometimes further simplification would still be needed afterwards. It depends on a case-by-case kind of evaluation. Finally, let's talk a little bit about verification. Verification, as we've done before, are mostly manual. We would take a look at the specification and then apply the specification on a pre-designed circuit by us to verify if it actually fits the specification. This is called manual verification, which sometimes can involve using the truth table, sometimes using the original specification to check if the behaviors are normal. Using the truth table, you will be able to cover most of the tricky places that might not be very obvious in the specification. But sometimes that can take a lot of time, especially when you have a very big truth table or just having a lot of input. So that's why sometimes, most of the times in real life, people would have to rely on using computer simulation to automatically go through the entire truth table. And these truth tables will also have to be automatically generated by a computer. This is called computer-assisted design in logical circuit designs. The details of these kind of automated verifications are kind of complex, and it's not within the scope of our lecture. It is important, however, for you to know that automatic verification do exist, and they rely on computer software simulation to accomplish the objective. Thank you.